So we'll start by looking at functions. So what exactly is a function? Before I define function, I'm going to define something else, and that is a relation. And a relation is simply, as I put there, a rule that maps between two sets of values. Bingo, there's an example. So it's mapping between these x and y values, and there's arrows going everywhere. You can see there's one going from -1 to -2, and then there's also one going from -2 to, where's that one going? Oh no, it's on the other side, 1 to 2. The question is, what is the rule for this map? Turns out to be x squared plus y squared is equal to 5. So a relation is any map you like, whereas a function is a specific type of relation. Okay. So it's unique in that it uniquely maps from one of the sets of values to another set of values. So you don't see the lines going backwards and forwards like the relation there. Everything's going from x to y. I put it in an x, I get a y. And so -2 there goes to 4, -1 goes to 1, and so on. That one is y equals x squared. That one's y equals x squared. Independent variable. So it's like the input of our function. So it's independent because we have free choice. We can put in whatever number we like, as long as it fits in what we call the domain of the function. Sometimes called the natural domain, natural domain, same thing really. So it's every possible value we could substitute into the function, and that becomes the domain of the function. Sometimes it's necessary to restrict the domain to certain values, and that might be a situation where we're only interested in, say we were doing the example I've got there, some experiment or something. And so really I'm only interested in positive numbers if my variable was time. So sometimes we might restrict the domain of our function. The dependent variable then is the output, because the answer depends upon what we substitute in, or the input. Range then are all the possible outputs. Every possible answer we could get substituting in every possible value in the domain. So what could the output be? And the notation we use, our function notation, doesn't have to be an f, of course. It could be any letter you like there. But what that's basically saying is y is some function of x where the independent variable is the x. That's what we're substituting into the function. And so f is representing the function. And once we substitute that in, we get the dependent variable, or the output. So y in this case represents the output. So as a simple example there, function x is 3x squared plus 4. Function 5 is saying, okay, input 5. It's just substitution, and the output would be 79. Don't have to substitute in a number, of course. If I substitute in a, all it's saying is everywhere you see an x, replace with a. So I get 3a squared plus 4. It doesn't have to be a single thing. So you see here I've got function x plus h minus function x. So first of all, everywhere I see an x, I'll put in x plus h, and then I'll subtract the actual function itself. Oh, there's some tidying up we can do there. Expand the whole thing out, pull it together, there we go. I end up with 6xh plus 3h squared. So how do we test whether or not a relation is a function? The simplest way is visually. If you know what the picture looks like, then it's a heck of a lot easier to work out these sorts of things, and we call it the vertical line test. Right? So if you were to draw a vertical line on our picture, as long as it only cuts it once, if at all, it'll be a function. So there's our hyperbola. Doesn't matter where I put that vertical line, yeah, it works. So yes, that is a function, as opposed to a sidewards parabola. No good, because look, I've drawn one and I've managed to cut it in 2 places. So it's not a function. In fact, that sort of relation is actually made up of 2 different functions. So y equals the square root of x, which would be the top half of the parabola there, and y equals minus the square root of x, which would be the bottom half of the parabola. So all right, domain and range. How do we find these things? So domain, what am I looking for? I'm looking for key things. And again, if you see the picture, it's a heck of a lot easier, because you can just read off the graph and you see, oh, that's the domain and the range. So if I have my sidewards parabola, I can see quite clearly that that graph only exists when x is greater than or equal to 0. substitute in a negative number, and we don't have an answer on our graph. One of these split functions that you sometimes see. So that one would have a domain of x is less than or equal to 0, and also x is greater than 3. Notice I used the word and there. So when you're talking about a domain, you're saying and. It's all of these things. As opposed to a solution to an inequality or an inequation, you would have or there because it would be impossible for a solution to be both less than or equal to 0 and also greater than 2 as well. So subtle difference, but technically we should be saying and in that situation for domain. All right, you don't know what the picture looks like. So all we've got is the equation itself, so algebra. What to look for? So key things, fractions, we look for those. We know the bottom of a fraction can never equal 0. So that's probably going to cause a problem in my domain. So there's the simple hyperbola. If all of a sudden I've had a mental blank, oh my goodness, what does that look like? I'd say, oh, hang on a sec. Bottom of the fraction can't equal 0. So x can't equal 0, so my domain is all real x, except x is equal to 0. Now there's a question about the grammar here. Do you put x equals to 0 or do I put x does not equal to 0? Because depending on your grammar, it could be either. Because you could be saying, oh look, it's all real x except x equals 0. I don't want to include x equals 0. But you might be saying, oh look, it's all real 0 except x can't equal 0. So really either is acceptable. It's just down to the grammar of it really. Not something you get hung up about, I suppose. Okay, so we have this particular one. What is it? Well, it's probably going to be some sort of hyperbolic curve of some description. Not sure exactly what without playing around with it a bit more. The key thing we want to know is the domain. Bottom of the fraction can't equal 0. So x squared minus 1 can't equal 0. So I know x can't equal plus or minus 1. Therefore, my domain is all real x except x is plus or minus 1. Remember, a domain is an inclusion, not an exclusion. So you could not write for that domain x cannot equal plus or minus 1. That's not good enough to describe the domain. Because I'll say, okay, well it can't equal plus or minus 1, but what can it equal? So you describe it completely. Two fractions, well, we got two different things to look at. I know x minus 1 can't equal 0, so x can't equal 1, and 7 minus x can't equal 0, so x can't equal 7. So all real x except those two particular points. Okay, another key thing to look for, square root signs. Because you can't find the square root of a negative number. So that's another key thing in the domain. So y equals the square root of 4 minus x squared. I know 4 minus x squared must be greater than or equal to 0. And if we solve that one, well, eventually x squared is less than or equal to 4, so x must be in between minus 2 and 2. I've got two square root signs. So x plus 3 must be greater than or equal to 0. So I know I can only sub in numbers greater than or equal to negative 3, but 5 minus x also has to be greater than or equal to 0. And that's telling me I can only sub in numbers less than or equal to 5. So combine the two, and I get x has to be in between minus 3 and 5. I got both a fraction and a square root sign. Well, the fraction's telling me the bottom of the fraction can't equal 0. The square root's telling me that x plus 2 has to be greater than or equal to 0. Combine the two together, then it's just x plus 2 is greater than 0. Because in this case, it can't equal 0. So x is greater than negative 2. What about the range then? What do we look for when we see the range? Again, visually, a lot easier. Because visually I can see that actually there's no breaks in that curve at all when I'm looking at it vertically. So it must be all real y. And don't just say all reals, by the way. Because if you say that, I'm going to say, well, hang on, x values or y values? You got to tell me. So it's the y values. And there's our split function. So for that one, it would be y is less than or equal to 1 and y is greater than 3. Don't know what it looks like? So algebraically, what do we look for? Maximum and minimum values. Can we tell that from our equation? So things like even powers, absolute values, they're always going to be positive. So that may well affect the possible answers. So y equals x squared, let's go to the simplest one of them all, I suppose. Y equals x squared, I know, well, hang on, y has to always be greater than or equal to 0. It's impossible to get a negative number as an answer. So if I have x squared plus 3, well, it's got to be greater than or equal to 0 plus 3. So therefore my range is y is greater than or equal to 3. So I know that 0 is a minimum value. 5 minus x squared, so this time it's going to be y has to be less than or equal to 5 minus x. If I'm subtracting the x squared, so y is less than or equal to 5. Absolute value of x plus 2, absolute values are always greater than or equal to 0. And similar idea, well, if I've got the absolute value minus 5, then it must be 0 minus 5. But I guess the other key thing to do with the range is that restrictions on your domain. Okay? So if I've got one, what am I going to do? I usually sub in the 2 endpoints to see what's happening at the ends of the domain, and the centre as well. Surprising how often these shapes are symmetric, so the middle is a nice one to look at and see what's happening. So back to y equals the square root of 4 minus x squared, we ended up with a restricted domain. We could only sub in values between minus 2 and 2. So x equals 2, that turns out to be 0. X equals 0, so the midpoint turns out to be 2. I don't think I bothered with negative 2 because we're squaring the x, so you're going to get the same answer as positive 2. So it looks like our range here is in between 0 and 2. And if you're unsure, sub a few more numbers in to confirm what you believe. In fact, that graph, if I was to draw it, would be, so it's actually our semicircle. Fractions. If you have a constant on the top of a fraction, it's impossible for that fraction to equal 0. You cannot divide a number by something and get the answer 0. Can't do it. So again, going back to our hyperbola, although all of a sudden we don't realise what it is. Hang on, I've got a fraction with a constant on the top. So I know y can't equal 0. So I'll rule y except y equals 0. 5 plus 1 on x, well, the fraction can't equal 0, so I can never get 5 plus 0. So I'll rule y except y equals 5. Ooh, okay, that doesn't have a constant on top. X plus 7 on x plus 4. But what I can do is simplify this down using a bit of polynomial division or however you choose to do it. I could rewrite that as 1 plus 3 on x plus 4. So there's the polynomial division. In case you don't see that straight away, you could always do your division and come up with the answer. So we know y can't equal 1 plus 0. So I'll rule y except y equals 1. Okay, so we'll start off looking at those sorts of ideas. Look,